Good day, I'm Dr. T and welcome to my office. So today I'd like to talk about chemical reactions, the changing of one chemical into another. And to do that, I really need to get some terminology out of the way. And the first terminology we should probably jump into is the chemical equation. Now, chemical equations are a way of representing what is taking place at the atomic level. So a chemical equation will start off with one or more, depending on how many players are involved, a chemical formula. Now, you can have empirical formula, molecular formula, structural formula, whatever is appropriate for what is taking place. These are separated by plus signs, and the pluses are pronounced as and. So I could have a reaction like silver nitrate and sodium chloride, and that would be the first part. These are what we call our reactants. This is what's going to be reacting together. You will also hear these called reagents. Reagents are a generic term for a chemical we use in the lab to do chemistry. When they're in the equation, it's more proper to call them reactants. They're what's going to react to then form. Next, we have an arrow in our chemical equation. If this is a one-way arrow, so it looks like a normal arrow, that's fairly straightforward. However, sometimes we have a two-way arrow. One that represents a reaction that can go both ways. And in reality, all reactions can go both ways, but some generally don't. So we'll first focus on those reactions that generally only go in one direction. Either way, the arrow is pronounced yields. So in our reaction, we'd have silver nitrate plus sodium chloride yields, and then the next chemicals are what we call our products. Those are the chemicals we get. So once again, separated by a plus sign, chemical formula, whichever formula is appropriate. So we would have silver nitrate plus sodium chloride yields silver chloride plus sodium nitrate. Now, more information can be added to our chemical equation. Chemical reactions don't actually destroy atoms or create them, and the chemical equation needs to represent this, that atoms are simply rearranging. So it's quite often the case where more than one molecule or formula unit of a particular compound is used in the reaction. The ratio isn't necessarily 1-to-1. To represent this, we will use what we call coefficients. Coefficients are numbers that exist right before the chemical formula and thus tell you the ratio that you have. Now, like the subscripts, we don't write ones, so if there is if there's only one of a particular chemical formula, we won't put a coefficient. So for example, we could have the reaction between hydrochloric acid and calcium hydroxide. So in this case, we would have an equation that would be 2HCl plus CaOH2 yields, and then to keep things balanced, 2H2O plus CaCl2, thus giving our ratios. And this is going to become incredibly important for us once we start doing chemical accounting, or what is more properly known as stoichiometry. The coefficients are going to start giving us the ratios, and we're going to be able to use those to know how much product is made or how much reactants are, a particular reactant is used. And thus, yay. Additional information within our chemical equation, which in this case is much more optional. Sometimes it exists, sometimes it's just not put in, are what's known as state symbols. State symbols are going to go next to your formula, and these are going to indicate the state that the particular compound is in. There will be a parentheses, and this is a full-size parentheses. A lot of people will put them in subscript, and that is not technically correct. I will do so as a bad habit myself, but once again, these are a full-size script, although lowercase. So state symbols would include, say, parentheses G parentheses, indicating that the preceding chemical was a gas, parentheses L parentheses, indicating it was a liquid, parentheses S parentheses, indicating it was a solid, all fairly straightforward here, and one that's a little bit of a curveball, parentheses AQ, close parentheses. This indicates it's aqueous, and by aqueous what I mean is it's dissolved in water. Water is such an important solvent for us, and the dissolving process is actually a little bit more advanced than simply the thing floating around, depending on what your compound is. This is an important state for us. So we're now able to think of the substance. Is it an aqueous solution, or is it sitting by itself? One feature you may end up doing is utilizing the balancing of an equation. So you may get an equation that is itself already balanced, but you also may have equations that are unbalanced. And in order to use them, you'll need to balance the equation. To do this, it's fairly straightforward, although it does take a bit of practice. The goal here is to indicate that the atoms have rearranged and none have magically appeared or disappeared in the process. We have what's known as conservation of mass, as you can't get rid of matter. And likewise, your atoms stay around. They just reshuffle. A couple of key things to keep in mind. What you're going to be changing is the coefficients. You can't change the subscripts. If you were to change the subscripts, you would be changing the fundamental chemicals in play. But you can change the coefficients as you are simply discussing the ratios of those chemicals currently in function. Generally speaking, I like to pick an atom at will. Polyatomic ions, as long as they're not being broken apart, there's still the polyatomic ion on both sides of the arrow, can be treated as one unit. So on our previous example, if I was to balance it, I would pick something like, say, the chlorides. Realize I have 1 chlorine in the reactants, 2 in the products, so I know I'm going to have to add a coefficient of 2 before the HCl. I can look at my hydrogens. In this case, it's going to be a little bit trickier, but I can think of water as HOH. And now, like, okay, I have 1 hydrogen on one side, 1 hydrogen, so it looks good to start with. But then when I balance the OHs, I realize, no, I'm going to have 2 HCl's and 2 waters. Yay. Simply look at the atoms, go back and forth, and you should be fairly straightforward. With that said, have a wonderful day.